Hello, my name is Carter Dudek.
And I'm Ryan Loeffler, and we're presenting our challenge for wind power. The basics of wind power, the process by which the wind is used to generate mechanical power or electricity. This is commonly harvested by wind turbines, and this is like when the blades turn, they spin a generator, which then converts mechanical energy into electrical energy. Wind power is a renewable source of energy harnessed from the movement of air. The first law of thermodynamics. Law of energy conservation, where energy cannot be created or destroyed. It can only be transferred or change forms. In wind power, the first law processes kinetic energy of wind into electrical energy while conserving energy. The kinetic energy is from the movement of the blades that spin in the wind, which is then the energy transferred into a generator. The generator allows for the energy to be distributed to homes and buildings that are connected to it. With respect to conservation of energy, it ensures that the total energy of a closed system remains constant. In the wind power, the energy is extracted from the wind and it must account for the energy lost due to the wind slowing down and the work done by the turbine.
The second law of thermodynamics. In the context of wind power, this implies that the wind turbine extracts kinetic energy from wind, but they cannot convert all of it into useful electrical energy. Some energy is lost due to the surroundings. The wind energy is converted into electricity. There is an increase in entropy of the system, representing the dispersion of energy, making it less available for useful work. It means that the upper limit to efficiently wind energy can be converted into electricity due to the second law's restrictions, represented by Bette's law, which defines the maximum theoretical efficiency of wind turbines. Wind turbines must operate with these limitations, striving to approach the maximum achievable efficiency, but recognizing there are some energy losses that are inevitable. Bette's law. Bette's law, formulated by German physicist Albert Betz in 1919, is a fundamental principle in wind power. It states that theoretical efficiency of a wind turbine is 59.3%, which means no more than 59.3% of the kinetic energy in the wind can be converted into mechanical energy to turn the rotor. The law's significance lies in its definition of an upper limit for wind turbine efficiency, helping engineers and designers understand the physical constraints of wind energy conversion. Bette's law serves as a crucial benchmark for the practical designs and operations of wind turbines, ensuring they operate as efficiently as possible with these constraints. The components of wind turbines and their impacts on thermodynamic efficiency. The rotor. The rotor is the part of the wind turbine that captures the kinetic energy of the wind. It consists of blades mounted on a hub, and its primary role is to intercept the wind and convert it into energy into rotational motion. The swept area is where more wind can be captured, maximizing the energy extraction. The generator. The generator is responsible for converting the mechanical energy from the rotating rotor into electrical energy. This is typically achieved through electromagnetic induction. The efficiency of the generator itself is a crucial factor. Higher efficiency ensures that the larger portion of mechanical energy is converted into electrical power. And the higher the efficiency, the more power you get from the wind turbine, which also creates more electricity. The tower. The tower provides necessary height to lift the motor above the ground level turbulence and take advantage of stronger and more consistent winds at higher altitudes. The tower's design and materials must balance structural integrity with weight considerations to optimize efficiency. The towers are usually at least 100 feet tall, even higher, so that they can be in the open. And usually they're in like plains in locations where there's really no trees at all. So the wind doesn't get affected. So the wind just pushes right into it and not disturbed by trees. The control systems. Control systems manage the operation of the wind turbine, adjusting various parameters to optimize performance and ensure safe operation. Adjustable blade pitch allows the turbine to optimize its performance under varying wind conditions, enhancing overall efficiency. This will allow, if there's no wind, it will, if there's like little wind, it will use as much optimization of the blades as possible to get some movement. If there's a lot of wind, they'll try to make the blades have more surface area, so it turns slower, but it has a longer lasting effect in the blades and the more power.
Overall impact on thermodynamic efficiency. The conversion efficiency. Wind turbines convert the kinetic energy of wind into electricity with typical efficiency rates ranging from about 30% to 50%. This efficiency varies based on the design, location, and maintenance of the turbine. Betts law limit. Betts law sets a theoretical limit of 59.3% for the maximum achievable efficiency of wind turbines, highlighting the physical constraints on energy conversion. Rotor and generator efficiency. Wind turbine efficiency depends on the rotor's ability to capture the wind efficiency and the generator's efficiency in converting mechanical energy into electrical energy. Operational factors. Efficiency can be influenced by factors like wind speed, temperature, and regular maintenance. Optimizing these aspects is crucial for improving the energy efficiency in wind power systems. Environmental impacts. The carbon emissions reduction. Wind power is a clean energy source that produces no direct greenhouse gas emissions, contributing to a significant reduction in carbon emissions and mitigating climate change. Reduced air pollution. Wind turbines generate electricity without emitting pollutants like sulfur dioxide and nitrogen oxide, improving air quality and public health. Conservation of resources. Wind power helps conserve finite fossil fuel resources and reduces the environmental impact of extraction and transportation. And the wildlife preservation. Properly sited wind farms and ongoing research focus on minimizing the impact on wildlife, emphasizing sustainable coexistence and conservation. Thermodynamic improvement. You can have the advanced blade design, which ongoing research focuses on optimizing blade shape, length, and materials to enhance aerodynamic efficiency and power output. Innovations like curved and serrated blades reduce drag and increase energy capture. Lightweight materials. Novel materials such as carbon composites are being used to construct lighter yet durable turbine components. Reduced weight leads to increased efficiency and lower structural loads on the turbine. Control systems. Advanced control algorithms and predictive maintenance systems use real-time data to adjust blade pitch, rotor speed, and yaw angles for optimal energy capture. This improves overall turbine performance and extends its lifespan.
Economic impacts. The initial investment. While wind power is cost effective in the long term, the installation and setup of wind turbines requires substantial initial capital investment. Maintenance costs, regular maintenance costs, and servicing are necessary to ensure the efficiency and longevity of wind turbines, including ongoing operational expenses. Grid integration. Integrating wind power into the electric grid may require infrastructure upgrades and investments to handle variable energy sources efficiently. Energy storage. To ensure a stable power supply, additional investments in energy storage technologies such as batteries may be needed to capture and store surplus wind energy for later use. Conclusion. Wind turbines operate within the principle of thermodynamics, specifically with the first and second laws. The first law governs the conservation of energy, ensuring that neither energy is created nor destroyed, but transformed from one form to another. In this case, wind turbines, kinetic energy is formed into mechanical energy as the rotor turns, and this mechanical energy is further transformed into electrical energy. Second law of thermodynamics highlights the limitations of energy conservation. It indicates that not all the wind's kinetic energy can be harnessed, setting a maximum efficiency limit defined by Bette's law. This restricts how effectively wind energy can be transformed into electricity. Wind turbines must operate within these thermodynamic constraints, striving to maximize efficiency while acknowledging the inherent losses such as mechanical friction and turbulence that limit their energy conservation capabilities. Understanding and optimizing these principles is crucial for advancing wind power as a sustainable and source of renewable energy. Here is our works cited, and thank you.